Good afternoon, all of you. In today's session, we are going to continue with CSIR NET JRF Chemical Science, June 2018, Part C, Series, right? So in the earlier sessions, we completed Part B, entire Chemical Science June 2018 discussion, and the different series of Part C were made, being it is the longer one, hence it is not possible to concise in a single video. That's why Part C is made into a different series. In each series, we have 10 questions, and the series 6, we are going to cover the last 10 questions of CSIR NET JRF Chemical Science, June 2018. Let us enter into our actual concept. So let us go with our question number 111. Question number 111. One of the correct normalized sp2 hybridized orbital is, here 4 options are provided to us. sp2 hybridized normalized equation we have to predict. So whenever sp2 hybridized orbital was considered, s percentage will be 33, where p contribution will be 66%. Okay, equation is in the form of a pi plus b pi. Okay, so whenever s orbital contribution is considered, 1 by under root 3 psi 2s will be taken, plus under root 2 by under root 3 pi 2px orbital contribution. This is for p orbital, right? So when we take sp2 hybridization, 1 s orbital combined with 2 p orbitals, entire orbitals are 3, s contribution will be 33, p contribution will be 66%, right? When we squaring these two components, 1 by under root 3 whole square is equal to 1 by 3 into 100. Now it is exactly matching with whatever s contribution given in sp2 hybridization. In the similar manner, under root 2 by under root 3 whole square when considered, it is given as 2 by 3 into 100. So its the percentage will be 66. P character here 66% will be there. So when we take this equation, 1 by under root 3 pi s plus under root 2 by under root 3 pi 2 px, it is matching with the contribution for s and p orbitals whatever actually given. So hence for question number 111, option number 3 will be the right answer. Let us move on to question number 112. The transition moment integral for rotational transition between j is equal to 1, m1 is equal to 0, j is equal to 2, m1 is equal to 0 states for diatomic molecule along z-axis is proportional to. Here, what transitional momental integral values are provided to us. If we apply the formula, integration limitations will be theta to pi is equal to integration pi theta is equal to 0 is given as, so y star j mj mu yj mj sine theta d theta d pi. This will be the empirical formula. When we derive the entire equation, the final answer will be theta 0 to pi cos square theta 3 cos square theta minus 1 d theta. This will be the right answer for question number 112. Transition moment integral for rotational transition. So this for the diatomic molecule due along the z-axis we have to consider, that will be calculated as this option number 1. Let us move on to question number 130. Assuming harmonic approximation, the energy change for the reaction HCl with deuterium molecule gives rise to DCl plus HD in centimeter inverse is, right? So when we are taking this reaction, reactants got converted into products. Reactants are HCl plus deuterium, products are DCl plus HD. So in this, vibrational frequency data is provided for individual molecules. HCl is given as 2885. Deuterium is given as 2990. DCl is given as 1990. HD is given as 3625. So this is about the vibrational frequency data provided for individual molecules, right? So we have to predict, energy change during the reactants into product. That energy change need to be calculated. In order to get that, the data provided will be taken, and energy change during the transformation of HD formation we are considering. This is given by bond dissociation energy plus bond association energy. Bond dissociation of HCl and deuterium and bond association of DCl and HD will be considered. Always dissociation denoted with negative, association given with positive sign, right? So in this, this transformation energy is given as minus EHCl plus ED2 plus EDCl plus EHD will be taken. So minus EHCl, that is minus 2885 minus 2990 plus 1990 plus 3625. When we add all these, when we do this calculation, the final answer will be minus 129. This is the energy of transformation, right? So for question number 113, option 3 will be the right answer. Let us move on to question number 114, the allowed electronic transition for fluorine molecule. When fluorine molecule was taken, we have to consider what kind of allowed transitions are possible. In order to give this type of transformation, we have to consider certain selection rules. Here, 4 selection rules are provided to us. Delta lambda is equal to plus or minus 1. Okay, so lambda change should be either plus 1 or minus 1 should be taken. And the second protocol will be gerade can be converted into ungerade. Ungerade can be converted into gerade orbital. So here parity should be changed. Change in the parity is required. That is the second protocol. Third will be spin retention. Either positive can be transformed into positive or negative can be transformed into negative. This kind of sign retention is required. And fourth one is lambda is equal to 0, 1, 2, 3. If value is 0, that is denoted with sigma. 1 is denoted with pi, 2 is denoted with delta, and 3 with pi. It is psi, right? So in this way, when 4 protocols are obeyed, then it is considered as a load transition. Let us see one by one. The first option, sigma to sigma. So when we are taking sigma, that is 0 value, and again sigma 0. But actual requirement is delta lambda is given by plus or minus 1. That is not obeyed by this one first rule. Hence, it is not allowed a transition. When we go to second, here also sigma to sigma not allowed. In third one, sigma to pi is allowed because sigma is a 0 state, pi is the first state. 0 to 1 state is allowed. That's why third statement is obeyed. Here, sign should be positive to positive or negative to negative. It is denoted as positive in the reactant. Here, it is after transition, it will be positive only because none of the sign is indicates there is a positive sign here, right? So that's why here plus to plus is possible, and parity should be changed, gerade to be converted into ungerade. That's why for question number 114, option number 3 will be the right answer. So let us move on to question number 115. Asymmetric top molecule among the following will be ethylene, allene, butatriene, and hexatriene was given. Among given the 4 options, allene will be the right answer from symmetric top molecule. When you consider allene molecule, it's bounded by carbon-carbon double bond and in either carbon-carbon double bond. Both the carbon-carbon double bonds are present in perpendicular manner. One of the double bond in horizontal plane, in either is in vertical plane. And it is of D2D symmetry. It is consisting C2, one vertical axis, and in either C2 is in the diagonal axis. And its symmetry elements are identical elements, CN axis, C2 perpendicular axis, and sigma D will be given. Its a point group symmetry is denoted with D2D symmetry, right? So because of all these, presence of all these, it is simply denoted as a element of symmetry. And the symmetric top molecule, because all symmetry elements are associated with this allene molecule. If you observe this, it is the cumulative double bond of system. Carbon-carbon double bonds are adjacent in nature. This is called a cumulative double bond. Two C2 axes which are perpendicular to each other, and here sigma diagonal plane is also present within the molecule. Hence, you can say it is of symmetric top molecule and non-dipole moment is provided. How can you say it is non-dipole? Because it is not a symmetrical molecule here. One of the double bond is horizontal, another double bond vertical plane. That's the reason why here mu will not be compensated. So it becomes IR active also. So 115, option number 2 will be the right answer. Let us move on to question number 116. A solution of iron plus 3 titrated potentiometrically using cerium plus 3 solution at 25 degrees centigrade. The EMF in volts. Redox system thus formed when 50% of Fe plus 3 and 80% of Fe plus 3 are titrated, would respectively. Okay, it is a kind of potentiometric titration, and where iron plus 3, cerium plus 3 got titrated. So that Fe turned into Fe plus 2, cerium plus 3 turned into cerium plus 4. Being it is a redox reaction, iron will be reduced while cerium will be oxidized. And two conditions provided: 50% of iron consumption, 80% of iron consumption. We have to predict EMF at that instances, right? So standard electrode potential of iron is provided as 0.77 volts. Log 2 value is given as 0.301. Let us apply Nernst equation. E is equal to E naught minus 0.0591 by N log of 1 by concentration of metal ion, right? E naught value is already known, that is 0.77. So when we apply this 50% consumption iron plus 3, so instead of concentration, we are taking the terms in percentages. How can